Hello, welcome to ATI 4205. This session will continue addressing the different inventory models used to calculate the quantity required to replenish inventory. In addition to the basic economic order quantity and the production order quantity models, the quantity discount and probabilistic models will be discussed, and examples will be provided. As stated in previous lectures, inventory models are used to determine the amount or the quantity of the items that should be ordered to replenish inventory. In addition, the previous sessions discussed the safety stock required to demand until inventory being replenished. The safety stock is the level of inventory available in hand that will determine when to order. Also, in a previous session, we defined the reorder point as the level of inventory which triggers an action to replenish that item in stock. Then we identified the formula used to calculate the reorder point, which will equal to lead time multiplied by demand per unit of time plus the safety stock. The quantity to be ordered can be calculated through the basic economic order quantity or production order quantity or quantity discount model. The basic economic order quantity and the production order quantity has been explained last week. This week we will go over the quantity discount model and the probabilistic model. And the probabilistic model, we use it in case that we are talking about probability of something happening for the demand, and that's why we use the probabilistic model, and we'll talk about that at later slides. The quantity discount model uses large quantity orders or purchases to negotiate and reduce items cost. A trade-off of having a large quantity in stock and the holding cost will occur. A reduced cost of large amounts purchased will increase holding cost because you are adding more to your inventory, and that will translate into holding cost. Now let's look at some of the terms, which is those terms we talked about before and we were defined before, but let's go back and repeat those terms. For Q, it's the quantity order. For D is the annual demand in units. For S is the setup or ordering cost per order. And for H is the holding or carrying cost per unit per year. And P is the price per unit. Then the total cost will equal to setup cost plus holding cost plus product cost. Or in other words, TC will equal to D over Q multiplied by S plus Q over 2 multiplied by H plus PD. Remember that the lowest cost when the setup cost is equal to the holding cost, which means that 2DS is equal to Q over 2H, which means that Q star will equal to the square root of 2DS over H. In this case, we cannot assume that the holding cost is constant when the price unit changes for each quantity discount. The more you order, the less the price is, so we need to take that into consideration. Thus, the holding cost is calculated as a percent I of unit price P. Replacing H with IP, the quantity model or the quantity formula will equal to the square root of 2DS over IP. Let's look at the following example. A typical quantity discount schedule for toy race cars shown in the table here in this slide. Ordering cost is $49 per order, while annual demand is 5,000 race cars per year. The annual demand. To analyze using a quantity discount model, we calculate Q star for each discount. If Q star for a discount does not qualify, choose the smallest possible order size to get the discount. Then compute the total cost for each Q star or adjusted value from the previous step. Then select the Q star that gives the lowest total cost. The first step will be to calculate Q star for every discount, assuming inventory carrying charge of I equal to 20%. This is given in the example. Since Q star is equal to the square root of 2ds over IP, based on that, we replace or we substitute the values of D and S, I and P within the formula, and we can get Q1 star will equal to 700 cars per order, Q2 star will equal to 714 cars per order, and Q3 star will equal to 718 cars per order. The first discount will start at 1000. So first, the 700 is without discount. That's the calculation for the item without discount, with $5. The first discount when you buy quantity of 1000, so we adjust the 714 to the first discount, which is the 1000, and we get the discount of $4.80 instead of $5, and we recalculate whatever the value is, and then the second discount we adjust to 2000 and then get the $4.75. So instead of 718, 2000. Now we need to calculate the holding cost, thus the total cost associated with each discount, and see if it's a good idea to order more than what we need and just put it in stock and pay holding costs for that. The annual product cost with no discount is equal to 5 times 5,000, and that is $25,000. The annual ordering cost will equal 5,000 divided by the quantity per order, which is 700 units. And once we divide the 5,000 divided by 700, we multiply that by the 49, which is the cost of one order, and that will equal to $350 as shown here. So the annual ordering cost for the first discount is $350 when we have $5. For the second one is $245, and for the third one is $122.50. The annual holding cost will equal to 700 units times 5, and that will equal to $350. And we do the same with the other discounts, and we will get an annual holding cost of $480 and an annual holding cost of $950. Now remember that we are not using the 700, we are using the 1000. So with 1000 multiplied by $4.80, we'll get $480. And with 2000 we are getting $950, and that's for the annual holding cost for these items. Now to get the total cost, we add, so we have 350 plus 350 plus 25,000, and that will equal to 25,700. For discount number 2, we'll get 24,725, and for discount number 3, we'll get 24,822 and 50 cents. Which means that the lowest cost, taking into consideration the trade-off with the holding cost, is discount quantity number 2, which is $4.80 when we buy 1000 units. Although the holding cost for Q star 2 is more than the holding cost for or of Q star number 1, the total cost is less, and for that we choose to buy 1000 unit. So we are not only looking at the holding cost, we are looking at the total cost, and here is cheaper than the first one. So we choose to have 300 items more on the shelf because we are getting less total cost for this discount. This diagram shows the lowest point of the total cost and the adjustments made to get the order quantity. And as you can see, here's the first one, which is at 1000, and we adjusted the point from here to here, and that was our new adjustment. And for the third discount, we had to move to 2000, and the point came up to here. So the lowest cost of all of them was this point, which is point B. That was the lowest total cost, and based on that it was chosen. When demand is not constant or not certain, we use a probabilistic model, and a safety stock need to be added or used to that model. So the safety stock will be used to achieve a desired service level and avoid stockouts. The reorder point will equal demand per day multiplied by lead time for a new order in days plus the safety stock that we added or we are talking about. So to calculate the annual stock out cost, if I don't have the item in stock, then there is a cost for that, and that will equal to the sum of the units short multiplied by the probability multiplied by the stock out cost divided by the number of units or cost per unit, and multiplied by the number of orders per year. Let's look at this example. An eyeglass frame company has the reorder point at or of 50 units, which is a daily demand multiplied by the lead time. That's the daily demand multiplied by the lead time. The stock out cost is $40 per frame. The number of orders per year is 6 orders, and the carrying cost is $5 per frame per year. The probability for the number of units is provided in the table. So when the number of units is 30, the probability is 20%, 40 is 20%, 50 is 30%, 60 is 20%, and 70 is 1%. The objective is to find the amount of safety stock that minimizes the sum of the additional inventory, holding cost, and stockouts. The annual holding cost is simply the holding cost per unit multiplied by the units added to the reorder point. For example, a safety stock of 20 frames, which implies that the new reorder point with the safety stock is 70, because we have already the reorder point at 50, which is the lead time multiplied, as we said in this one, demand multiplied, daily demand multiplied by the lead time. So now we have with safety stock 50 plus 20 is 70, and that raises the annual carrying cost by 5 multiplied by 20, and that's 100 because we have 20 more than the reorder point, which is 50 that we have. As stated before, the annual stock out cost equal the sum of the units short multiplied by the probability multiplied by the stock out cost per unit multiplied by the number of orders per year. So if the demand is 70 and the safety stock is 10 only, 10 plus 50, that's 60. So we have a short of 10. With a short of 10, that is a probability of 0.1, and that will be multiplied by $40. That's the cost of stock out per frame, and then we have 6 orders, which will equal to 240. If the safety stock is 0, we don't have anything, then all what we have is the 50 with 50, then we have two options. Either the demand is 70 and that will cause a shortage of 20, or a demand of 60 and that will cause a shortage of 10. So when it's 60, 10 multiplied by 0.2 multiplied by the $40 multiplied by 6. When it's 20, it's 0.1 multiplied by 40 multiplied by 6. We add those and that will give me the 960 with 0 holding cost, because I don't have anything additional. Whatever the reorder point, whatever the 50 that I have has been used. So 0 holding cost, but we have stock out cost of 960. So the total cost will equal to 960. So with 20 extra units in stock and considering the associated holding cost will be still cheaper than having a shortage or stock outs. So if I have 0 safety stock, then the total cost will go up way a lot than having 20 in inventory and paying a holding cost on that. In some cases, the manager will define a service level of 95% of the demand, or having stock out of 5% of the time that the service is being provided. So it's 95% level of confidence that we are going to service our customer or to fulfill the demand for our customer. Assuming demand during lead time follows a normal curve in these kind of probabilistic distributions or curves, then we have a certain distribution that follows. So assuming that we have a normal curve or normal distribution with known mean and standard deviation, then the reorder point can be calculated using the following formula. The reorder point will equal to demand during lead time plus Z, and Z is a number of standard deviations, multiplied by delta DLT, and that's the standard deviation of demand during lead time. The curve in this graph shows the 95% probability of no stockouts. This is the 95%, and that's the area under the curve, while the 5% is the risk of stockout, which is the area under the curve here at the end of the normal curve. So Z is the number of standard deviation, will assist in finding the safety stock required to keep demand fulfillment at 95%. How much variability I have to have in stock, and that's the safety stock. Basically, we are saying how much more can I have over the mean, which is 350, to be safe and fulfill the demand of 95% as the manager wants. So the following example shows exactly how that works. So if the average demand mu is equal to 350, that's the median or the mean. The standard deviation of the demand during lead time is equal to delta DLT, which is 10 kits, and with 5% stock out policy or 95% service level required, we use the Z table. Z table is in statistics, mostly in most of the statistical books or statistics books. At the end of the book, you can find the Z table that will show you the 5% Z value and or 95% level of service Z value, which will equal to 1.65. So it's Z is predetermined in tables at the end of the book based on the level of service that will be required. So safety stock will equal to Z multiplied by delta DLT, which will equal to 1.65 multiplied by 10, and that is 16.5 kits. The reorder point, it's the expected demand during lead time plus safety stock, and in this case 350 plus 16.5 kits of frame of safety stock. So that will be a total of 366.5, or of course, we cannot split units here, so we can say that it's 367 kits. The order will be placed as soon as inventory gets to 367. By the end of the anticipated lead time, the order will be received. The 16.5 safe stock units will work as a caution to cover any delays or issues in receiving the shipment. When data on demand during lead time is not available, there are other models available, 3 models available. When demand is variable and lead time is constant, when lead time is variable and demand is constant, and when both demand and lead time are variable. Those are other probabilistic models that we are not going to address in this semester, but just for you to know that there are other models that can cover the demand, and that will be based on whatever approach we are using, whatever variables we are using, and based on that we can choose the approach or the model appropriate for that. That will be all for inventory control. If you have any questions, please let me know. So that's the end of the session. Thank you and have a great day.